Right, so in the previous section, or a couple of videos, we're looking at dimension reduction algorithms that are part of unsupervised algorithms, right? And now we're moving on to the clustering types of unsupervised algorithms, and we're just going to knock them to discuss them in one video. The first, so just a general part about clustering. So clustering is when we are grouping similar instances of data in such a way that instances that are similar, they are close to each other, and instances that are not similar to those instances are further apart. So these instances will be similar, they're in one cluster, and these will be in another cluster because they're similar, but these two groups are dissimilar, so they have to be separate. And for us to do that, I mean, there are so many use cases for this. Let's say you want to segment your client base. You want to segment your client base, you can do that because maybe there's a product that you want to sell to the clients, and you can't just sell to everyone. You want to sell to a particular type of client who behaves in a particular way. But for you to figure out who those clients are, you might cluster them. You'll be like, oh yeah, so these are behavior number 1 and these are behavior number 2. So which behavior are you going to go for? I'm going to go for clients who have behavior number 2, and you sell the product to only these clients. So how do you come up with these clusters? These are the algorithms we're discussing. And the first one is going to be k-means. I think you've heard this before. If you've done any supervised learning or any bit of machine learning before, you've heard about k-means. So k-means is we first start off by specifying how many clusters we want. In our example here, we have 2 clusters. So you first specify that I want my k to be, let's say 2, 3, 4, 5, or whatever it's going to be. And after doing that, the algorithm, it randomly assigns each instance to exactly one of the k clusters. So in that case, it will say, oh yeah, I'm randomly, for this observation, I've randomly allocated you to 1, or randomly allocated it to cluster number 2 and stuff like that. When it is randomly allocated, it calculates something called within cluster variation. Within cluster variation. And what the k-means does, it tries to optimizes the grouping by minimizing within cluster variation. Minimizing. So it minimizes within cluster variation. So when we have randomly assigned, it calculates the within cluster variation, and then it tries to minimize that within cluster variation, also called the inertia. It's also called the inertia. It does that such that the sum of the within cluster variation across all clusters is as small as possible. So here it calculates the within cluster variation, it adds them up. It gets the sum. When it gets the sum, it gets a result here. And then it tries to shift things around. When it shifts things around and it has lowered it, it keeps that state. So it tries to optimize, to move things around to lower the sum of within cluster variations. That's what it does. So it randomly assigns each observation to one of the clay clusters and then begins to reassign these observations to minimize this within cluster. But what is it? It's the Euclidean distance between each observation and its center. That's why I was putting these lines here. So it calculates the Euclidean distances here within the center. And then we'll be like, nah, there's too much variation here. I assigned this observation to this cluster. Maybe I made a mistake. This is just too high. This observation probably belongs to that cluster. Or if there's a third cluster here. So it then calculates the Euclidean distances and then reassigns the observations. What this means then is after it is done, it hopefully has the lowest sum of within cluster variations, and then it's happy. It has assigned the clusters to the right, it has assigned the right observations to the right clusters. So, but if you've paid attention, right, what happens is there is something wrong, something not like wrong, but there's something that is a problem with k-means. It randomly assigns, when it starts, instances. It randomly assigns instances to clusters. And when it does that, if you run it again from scratch, its randomness is probably going to assign the instances to different clusters when it starts. So that means different runs of k-means, different runs result in different clusters. It's very high, the probability is very high that different runs will result in different clusters. But what you can do is you run it multiple times. You run k-means multiple times from start to finish, and then you are recording each run. You are recording the results of each run and the clusters for each run, and the within cluster variations, the sum of the total of the within cluster variations, and you choose that run that had the lowest total sum of within cluster variations. When you choose that run, maybe you ran it 5 times, and maybe run number 3 at the lowest total within cluster variations. You'll be like, okay, cool, I'm going to choose the cluster that were created by run number 3. So that's what you can do. So it's very important. This is very important. K-means needs you to choose the number of k. How many clusters do you want? 10, 20, 10, 5, 100, or whatever it's going to be. There are some methods that will help you choose the number of clusters, like your silhouette plots and stuff like that. We'll see them when we get them. But that's but those are not selecting for you. They're just giving you an idea, and then you have to select for yourself. You select, okay, I want to create 5 clusters. When you tell the algorithm you want to create 5 clusters, it initially just randomly assigns instances to the clusters and starts calculating the within cluster variation and starts optimizing it, moving things around to make sure that to minimize it. When it has reached the absolute minimum, or the minimum that it's happy with, it stops. It's like, yeah, I've assigned to the clusters. You can rerun it. It starts the whole process again, randomly does it. You rerun it, randomly does it, and optimizes, randomly optimizes, and then you can choose the run that is the lowest total within cluster variation. So that is k-means. The second one is hierarchical. The second one is hierarchical clustering. What is hierarchical clustering? So this one, what happens here is you really do not need to choose a k. You don't need to choose a k. What happens is, I'm going to talk about the most famous one, which is agglomerative clustering. It uses a tree-based clustering method and builds something called a dendrogram. So let me see if my thingy will work now. It'll create a dendrogram. Okay, so it has worked. Let me see if I can move this thing. Yeah, cool. So it creates a dendrogram like this. So let me explain what is happening here. This is an upside tree. It's an upside tree. You can see these are the leaves. These are the leaves, and these are the branches, and this is the root of the tree. So it starts here, at the bottom here, and at the bottom here, it starts there at the bottom, and then starts joining things. As you can see, I think you can see that the lines are joining. So what it's doing is, it starts here at the bottom, and right at the bottom we have our instances in our data, our individual instances. So these are individual points, which are individual instances. And what it does is, it groups the instances that are similar. It looks at the instances and says which ones are similar, and then it joins those instances. Joins the instances that are similar, and then goes up again. It says for those groupings of the 2 instances, which 2 groups are similar, it finds them, it groups them. And then for those groups, there are now 4. For the groups of 4, which ones are similar, it groups them into groups of 8. For the groups of 8, which ones are similar, into 16, into 32, and stuff like that. So it groups instances as it goes up the tree like this, up the tree, until it gets to the top part. to the top part here, it has grouped all the instances into one cluster, into one grouping. It has grouped everything. So here it starts off with the individual ones, groups them to make groups of 2, groups according to how similar they are. And then it's like, okay, for the groups of 2, I will then group the groups of 2 into groups of 4. It puts them together depending on how similar those 2 groups are, going up the tree. And this is an iterative process, as you can see. It's an iterative process, and all the instances are eventually linked together, forming a single trunk of the tree. Once hierarchical clustering is finished, you can view this dendrogram. You can actually plot it. You can view the dendrogram, and when you view it, you can now determine where you want to cut the tree. So if you cut the tree at this position here, all the different branches are actual clusters. So you see, we've cut these branches into 1, 2, 3, 4, 5, 6, 7, going all the way 9, 10, 12, 15, 20, 25, 30, or whatever it is. All these branches here, those branches are your clusters. So you choose where you want, you choose the height where you want to cut the tree. If you cut it very low here, you're going to have many clusters. If you cut it up here, you're only going to have 1, 2, 3. So here you're going to have 3 clusters. At the bottom here, you're going to have maybe 57 clusters, or whatever it's going to be, whatever number is going to be. You're going to have so many clusters at the bottom here. Here you have 1, 2, 3, 4, 5 clusters. So that's what you choose in hierarchical clustering. You just let it run, it runs, it finishes until it gets to one cluster. When it gets to one cluster, you draw your dendrogram, and then you start to make a decision. Where do you want to cut? What height are you going to cut it? What height are you going to cut it? That height is similar to choosing like the K in our K-means. It's almost similar, but different principle. So that is hierarchical clustering. And then the third type of clustering is third and last is DB scan. DB scan, which is density based spatial clustering of applications with noise. Yeah, density based spatial clustering of applications with noise. DB scan. Very good name. Long, but yeah. This is more powerful and is based on density of points. If you have done physics before, you know that density is measured as mass per unit volume. So it's almost similar. It's analogous actually. Mass per unit volume. So what happens is, given all instances we have in space, like we have all points in space, all our observations in space, right? DB scan will group together those that are pegged closely together, where close together is defined as a minimum number of instances that must exist within a certain distance. Very, very important. So here we have minimum number of instances that must exist within a minimum distance. So we specify both the minimum number of instances and the minimum distance. If an instance, if an instance is within, let's say this instance here, it is within a specified distance of multiple. Okay, so first let me just talk about this. An instance is going to be like, okay, so we are going to have these instances together because they are within a minimum distance. Like this is going to be the distance that we are not like a minimum distance. It's supposed to actually be a certain distance or a maximum distance. It's actually maximum distance, within a maximum distance. So that's why I'm drawing this border. Within these, they're going to be in the same cluster. For this point here, they're going to be in this cluster. Right? Let's say there's a point here. Oh yeah, let me put it there. And it's within 2 clusters, as you can see, because there's this distance as well. So if an instance is within this specified distance of multiple clusters, it will be grouped with the cluster to which it is mostly densely located. So the one that is denser, if in here there are like 50 points and here there are 20 points, we'll put it to be with that cluster that is denser, that has more points, and not the one that has 20. All right? And any instance like this one here, any instance that is not within this specified distance, as you can see, it's not within any specified distance, it is called an outlier. It is not within a certain distance. It's not within a maximum distance of any one of those clusters. So this one here is called an outlier. So unlike k-means, there's no need to specify the number of clusters. We just specify the minimum number of instances that should be in a certain distance. What that then means is, here we can have 20, here we can have 5, here we can have 50, here we can have 10 observations that are in those clusters. So this means that we can have so many different shapes of these clusters. It is flexible. It has so many different shapes that we can create because it has a restriction. There's a restriction. The distance one is putting a restriction on how we create these clusters. The advantage of this over something like k-means is because this outlier does not affect the clusters. It doesn't. Outlier, you're outside our distance, we do not care. But for k-means, the problem now with k-means is it tries to run everything. So imagine there was a point here. It was going to try to minimize this by putting this point along with some other cluster, you know. And when it then calculates the Euclidean distance, it's going to be a problem because this is an outlier. So k-means is very prone to outliers, but dbScan is not, because it has that restriction of maximum distance. Dude, if you do not fit the maximum distance, you can't sit with us. You're outside. We'll call you an outlier. And like we said previously in some of the videos that we said before, when you figure out the outliers, you can then put the outliers through a different, let's say, supervised model to the ones that you are going to use for these ones that are being clustered or something like that. So, but that is what dbScan does. In the next video, we're going to quickly look at feature extraction and supervised learning models, and then after that, we are going to briefly look at unsupervised deep learning, and as highlights like this. So don't be scared. And then for the last part, we are going to look at just anomaly detection. What does it mean to do anomaly detection? What algorithms can we use? So stay tuned for that video, for the next video, which is feature extraction.